The James Webb Space Telescope, also known as the JWST, finally launched on December 25th for its journey of 930,000 miles from Earth. This is the next generation that will replace the famous Hubble Space Telescope. Hubble has been capturing awesome photos for over 30 years, but it's time for something better. In this video, we're going to discuss James Webb Telescope discovery sparks excitement for climate study on other planets. The video is going to be amazing, so make sure you stick to the end. Before starting the video, be sure to smash that like button and subscribe to never miss out on any of our videos.
NASA's James Webb Space Telescope, remember, was launched from the northeastern coast of South America.
A successful step on its journey to a point 1 million miles away from Earth today.
NASA releasing a full batch of images and data from the massive James Webb Space Telescope.
$10 billion machine.
Thousands of galaxies that we didn't know existed.
The JWST will be tasked with using its infrared sensors to explore some of the most distant and hard-to-see parts of the sky, helping with the search for exoplanets and with exploring the earliest days of the universe. So this seems like a good time to go over the most important scientific concepts that relate to space telescopes. Carbon dioxide in an exoplanet atmosphere. The James Webb Space Telescope has provided the first clear evidence of carbon dioxide in the atmosphere of a planet outside the solar system. This observation of a gas giant planet orbiting a sun-like star 700 light-years away provides important insights into the planet's composition and formation. The finding, which is accepted for publication in Nature, also indicates Webb's unique ability to detect and measure carbon dioxide in the thinner atmospheres of smaller rocky planets. WASP-39b is a hot gas giant with a mass roughly 1/4 that of Jupiter, about the same as Saturn, and a diameter 1.3 times greater than Jupiter. Its extreme puffiness is partly related to its high temperature, about 900 degrees Celsius or 1170 Kelvin. Unlike the cooler, more compact gas giants in our solar system, WASP-39b orbits very close to its star, only about 1/8 the distance between the Sun and Mercury, completing one circuit in just over 4 Earth days. The planet's discovery, reported in 2011, was made based on ground-based detections of the subtle periodic dimming of light from its host star as the planet transits or passes in front of the star. Previous observations from other telescopes, including the Hubble and Spitzer space telescopes, revealed the presence of water vapor, sodium and potassium in the planet's atmosphere. Webb's unmatched infrared sensitivity has now confirmed the presence of carbon dioxide on this planet as well. Filtered starlight. The atmosphere scatters and absorbs some colors more than others, depending on factors such as what the atmosphere is made of, how thick it is, and whether or not there are clouds. Because different gases absorb different combinations of colors, researchers can analyze small differences in the brightness of the transmitted light across a spectrum of wavelengths to determine exactly what an atmosphere is made of. Transit authorities. TRAPPIST-1, the system's parent star, is dim and small, around the size of Jupiter, but not dim enough to directly image its planetary system. The planets are too close to their star to revolve, even with a large telescope like JWST, so we'll still be relying on the transit method, Burgasser says. However, JWST will allow us to search not just for starlight blocked by the planets, but starlight that filters through their atmospheres, which will allow us to measure the temperatures and chemical compositions of those atmospheres in more detail, necessary to search for life. This technique is called transit spectroscopy and will be the main approach used to study the atmospheres of the TRAPPIST-1 system through the JWST. Deck explained to us how it works. When a planet passes in front of a star, it blocks light from that star, she says. A bigger planet will block more light. If a planet has an atmosphere, that atmosphere extends the size of the planet past the size of the rocky core, and so planets with atmospheres block additional light compared with those with the same size rocky core without an atmosphere. The key point is that the atmosphere only blocks the light of certain colors or wavelengths, which correspond to particular wavelengths of light that excite particular molecules in the atmosphere. Effectively, JWST will look at a host star with different filters on, isolating particular colors of light from the star. When the transit happens, the amount of light blocked by the planet will be different in each of the filters, depending on which molecules are present in the atmosphere and on other characteristics of the atmosphere. Alien life. When the public speaks about alien life, we often conjure images in our heads of Hollywood movie monsters, intelligent creatures with ray guns and incredible tech.
We're looking at the first incontrovertible proof of life beyond Earth.
However, we rarely consider the more grounded and scientifically likely kind of alien life, which would be, on a microbial scale, single-celled organisms and other forms of simple life are much more believable than the usual trappings of sci-fi. But why do scientists believe the JWST might find even microbial life? The belief that simple life, like the earliest forms of life on Earth, might exist on other planets finds a bit of support by looking back even before we look up. Life started so quickly on Earth, Dr. Rugheimer said, in some of our oldest rocks, we already have evidence of life. We have really robust evidence of life dating back 3.5, maybe 3.8 billion years, and this is right after the planet cooled. In other words, almost as soon as there could be life on Earth, there has had it been taken until recently in Earth's history that could cause more pessimism about foreign microbial life. However, looking at Earth's timeline transitioning from no life to life, as Dr. Rugheimer put it, supports the argument for searching for microbial life elsewhere in the universe. Previously, Dr. Rugheimer explained how the JWST can analyze exoplanets to determine what's abundant in their atmospheres. Depending on what the JWST sees, certain planets may or may not be indicative of life. Ozone and methane, for example, are a combination that suggests life. Hypothetically, if an alien astronomer looked at Earth with an infrared telescope like the JWST, its best bet for knowing we're here would be detecting ozone and methane in Earth's atmosphere, in addition to habitability signs of water and carbon dioxide. Oxygenic photosynthesis uses carbon dioxide, water, and light from the sun to make the oxygen we breathe. Ozone comes from oxygen, so detecting either would be interesting, and methane is produced in quantities 100 times more by life than by geology. Ice giants. Far-flung Uranus and Neptune, the ice giants of our solar system, are as mysterious as they are distant. The cold and remote giant planets Uranus and Neptune are nicknamed the ice giants because their interiors are compositionally different from Jupiter and Saturn, which are richer in hydrogen and helium and are known as the gas giants. They represent the least explored category of the planet in our solar system. Scientists use Webb plan to study the circulation patterns, chemistry, and weather of Uranus and Neptune in a way only Webb can. The key thing that Webb can do that is very difficult to accomplish from any other facility is map their atmospheric temperature and chemical structure, explained the study's leader, Fletcher, an associate professor of planetary science at the University of Leicester in the United Kingdom. We think that the weather and climate of the ice giants are going to have a fundamentally different character compared to the gas giants. They're so far away from the sun. They're smaller in size and rotate slower on their axes, but also because the blend of gases and the amount of atmospheric mixing is very different compared with Jupiter and Saturn. All the gases in the upper atmospheres of Uranus and Neptune have unique chemical fingerprints that Webb can detect. Crucially, Webb can distinguish one chemical from another. If these chemicals are being produced by sunlight interacting with the atmosphere, or if they're being redistributed from place to place by large-scale circulation patterns, Webb will be able to see that. Let us know your opinion in the comment section below. This was all for today. Hope you liked the video. Don't forget to subscribe to our YouTube channel. Stay safe, and we'll be back soon with another video just for you guys.